Hi again. On this one, we are going to try and divert the code from access denied to the access granted branch. I know the code looks weird with the heap allocation, but bear with me, you'll understand in the end of this video. So, to do this, we're going to try and manipulate the equal boolean referenced by the pointer in the stack. You can do this in one of two ways, and I'll make sure to highlight their differences in the end of this video as well. The first way is for you to find the address you want to write to in the stack, so let's dump some of it. As you can see here, there are a few of what looks like memory addresses, but we're not really sure of that. So let's look into GDB. So when you look into the main function, you can see the string compares testing the return value, then setting edx, the lowest weight, appropriately, and then placing that true or false result into whatever EAX is pointing at. And if we look at what EAX is holding, it's holding a pointer stored to EBP minus 210 in hexadecimal. EBP minus anything is local variable, and plus something is a parameter sent to the function, as the stack is usually set at the function prolog. So this is a local variable and therefore must have been initialized in the beginning of the function. And there you go, the memory address we are interested in. If we go back now to the dump data from before, we can easily see that the pointer is dumped and in position 1, 2, 3, 4, 5, 6. That's great. I now know where I want to write to. But how do I write to that memory address? To do that, you need to use the %n specifier. This is quite a unique one, as it doesn't read from the current position in stack, but instead writes whatever number of characters have already been printed out by the current printf to the position in memory currently referenced in stack. If it's the first time you hear this, it can be a lot to process, so let's see it in action. This example will hopefully also shed some light regarding why coming up with this option. Some old school table formatting in terminal windows, I reckon. Here you can see that right before the word ninja, there's a %n, and what that does is store the number of characters already printed into the value pointed by variable I, which is then used to space out the next string, turtle, on the next line to match ninja on the previous line. This part might also be a first for you, but I'll leave it to the printf man page as it's not needed for format string exploitation to be understood. So let's now see this in action in our vulnerable code. Again, in the 6th position, so let's confirm it using direct parameter access. Now, according to what we saw with %n, if I were to simply change the specifier here to %n, it would write a 0 to that address, which is considered a false value and therefore will deny us access. Now, if I were to write one character first, it would then write the value 1, which would be considered a true value, and there you go, access granted. Okay, so I mentioned before there were two ways for you to write to a memory position. The second one is again using the %n, but now instead of relying on finding the address on stack, we will provide it ourselves in the payload we're injecting. As you might imagine, this does provide you with more flexibility in terms of options of where to write to. So why bother with learning about the first way? There's a huge advantage to the first way, which is its ability to bypass ASLR. If it sounds confusing, don't worry, I'll explain with a practical example in the end of this video, after you understand this second technique. So let's jump into it. You first need to realize that if you place a value in the injected payload, it will be accessible using direct parameter access. That, of course, assumes that the string is stored in the stack, as it usually is put into a local character array when it comes to CTFs at least. As you can see in the code, the string you're injecting will be placed in the stack. So let's look at where would a 4-byte value be accessible to direct parameter access. To do that, we place a recognizable value, 4a's, and then start dumping the stack to see where it's at. As you can see here at 1, 2, 3, 4, 5, 6, 7, there's the 4a's in hex. So at this point, I know that if I place a memory address in the beginning of my string, it'll be accessible by me using $7$X. This means that if we were to manipulate the equal variable to change it to true again, using this technique would be like this. If you remember, the pointer to the equal value was in the 6th position, so let's grab this value and replace the 4 A's with it. First, let's confirm we access exactly that pointer. And there you go. Now, if we just replace the X for N, it will write the number 4 since the memory address we have printed so far has that length. Since 4 and any value other than 0 is considered true, it grants us access again. Finally, I mentioned there was a difference between finding the address in the stack and manually injecting it in the payload. To better understand this, I had the equal value placed in the heap, a position in memory that is randomized by ASLR. And now we'll enable ASLR and see this in action. After accessing the 6th position in the stack, you can see that it changes now. By the way, given the clearly poor randomization on the system, another way to do this would be to brute force the position, which shouldn't take more than 30 seconds. There you go. However, not the point here, so back to the 6th position where we found the pointer in stack. We can simply use the same payload as before when it was static, because it doesn't matter if the pointer changes due to SLR, since its relative position in the stack is still the same, which is 6. Now, the challenge is to have greater control over exactly what we write. As you might imagine, if we want to write a typical memory address, that could require us to write hundreds of millions of characters, which is obviously not feasible. See you in the next one.